Now it's recording. So yeah, the question we are going to address today is how to speed up the address translation. And avoid the extra memory in paging. So we still want to use paging, but we want to avoid this extra memory lookup which arises because of the page tables. Okay, good. So generally, when we want to make things fast, we want some hardware support. Like in case of context switch you saw, like in case of base bounds register for segmentation and so on. Okay, so here we'll use something called translation Lookaside buffer. Which is in short called TLB. Okay, and this is actually a hardware which is part of MMU, Memory Management Unit. Okay, and this is just a fast hardware cache. So I hope you are familiar with the concept of cache. It's just a fast memory, physical memory. And this is used to, so this is a cache of what? Of popular virtual to physical address translations. Okay, good. So since this is just a cache, another name for it is address translation cache. Okay, so what is going to be the idea? So this will have some translation. This cache will have some translation. So on each memory reference, the hardware first checks the TLB. Okay, to see if it contains the translation. And if that happens, the translation is performed quickly without needing a memory lookup. Okay. So TLBs are actually what make virtual memory possible, because otherwise it would be too slow. So it is said that they realize the virtual memory in a way. So they are essential for realizing virtual memory. Okay. So okay. So since they are that important, let's look into their algorithm. So last time we saw the algorithm in case of what to do for page tables and how the page translation happens by hardware. So we'll see how that gets modified in case of TLB. So it's not going to be much different. So first step is going to be the same. First you extract the VPN. So you AND it with the VPN mask and shift it by the offset. Second step is going to be now you check in the TLB. So success, comma TLB entry is going to be you do a TLB lookup by the VPN and see if it is there. If so, you put success is equal to true and TLB entry to be the TLB entry. We'll see what a TLB entry is in detail slightly later. Third, if success is equal to true, so this is called a TLB hit that you have found the desired VPN translation in the TLB. So in that case, you just check whether you can access it, if it's valid, and like so. Let's say if you can access TLB entry dot protection bits is equal to true, then you just put the offset. So you then extract the offset by ANDing the virtual address with the offset mask. And then, yeah, so this is the offset that you get. And then you find out the physical address. So this is the same process that we had last time. So this is TLB entry. You extract the frame number from it, PFN. And this, you shift it by the PFN shift. And this you then OR with the offset. Okay. And now you have arrived at the physical address. So now just load the register with whatever that physical memory address contains. Okay, so this is what happens in case of a TLB hit. Okay, now, okay, so first, like, let's put an else here for protection fault. That if this was not true, then you raise an exception. And then you come to the else part. So this else part is called a TLB miss. And here what you do is what you did whenever, like for the usual address translation, you go to the page table. So again, you find out the page table entry address is equal to the page table base register plus VPN. Sorry, this VPN should be offset. No, this should be VPN, of course. Yeah, this we did last time actually, because the page table is indexed by the VPN, so each of its entries correspond to one virtual page. So VPN into size of page table entry. So by doing this, you reach the page table entry, and then you access the memory to get the page table entry. Okay. And now if this is valid, if this is not valid, then there is exception. Seg fault. If the protection bits can access. Then you raise another exception. Protection fault. And now if all this does not happen, then you actually go and insert in the TLB VPN, comma, pte.pfn, and then maybe pte.protection bits, etc. And then what you do, you just retry the instruction. So retry instruction, is it outside blue? Here. Okay. So this is the control flow of the TLB. So this is the algorithm. So I mean, it might look like a long one, but actually conceptually it's very easy. What it does is that first extract the VPN, then look in the TLB. So this part is looking into the TLB, if it is there or not. If the TLB is hit, then you just check the protection bits if you can access. Then you compute the offset, you compute the physical address, and you load the register from the uh, desired physical address. Otherwise, you raise some exception. And if it is a TLB miss, then the hardware calculates the page table entry address from the page table base register, adding the offset into the page table by using the VPN times the page table entry. And then it goes there, accesses that memory, sees whether it's valid, protection bits are fine, and if all these things are fine, then it copies the pastable entry into the TLB. Okay, so this is the idea of the TLB, and so any questions about this algorithm till now? So this part, the later part, TLB miss part, a lot of it we have seen like in the previous lecture, and even the TLB hit part. After that, whatever is done was there, but it was done after calculating the after going to the TLB entry. So now, like there is a kind of reshuffle that has happened. Okay, so this is what happens in case of TLB. Okay. Okay, good. So, what is the basic principle of the TLB? That usually the address translation will be in TLB. This is what is desired. This is what we want to happen. And because of this, this would cause less overhead. Okay. And why it will cause less overhead? Because TLB is a fast hardware cache situated near the processor, basically on the memory management unit. Okay, so if misses happen, so then this will cause, yeah, is there a question, Shubhlingam?
No, sir, that was very so.
So this will cause a memory lookup, okay, and that will make things slow. So what our aim is going to be, the aim is going to minimize TLB misses, okay, as much as possible. Okay, so I hope the general principle of the TLB is clear, that, and the general methodology is clear, that what is going to happen, okay, or how it works. Okay, good. So let's see an example and see how it can actually work in practice, and why it can like actually speed up things. So let's take an example to be an array access. Okay, so let's take size 10 array of integers. So integers are like 4 bytes. And let's say that the array starts at virtual memory 100. And let's say that the address space is just like 8 bits. So this is like 256 bytes. Okay. And let's say that the page size is really small, is let's say 16 bytes. So how many bits per page now? So how many bits per offset? If the page is 16 bytes, how many bits per offset? Okay.
4 bits.
Okay, I expect an answer.
4 bits.
4 bits per offset. And so, and then the VPN is going to be, and the number of pages in address space is going to be how many pages in address space?
2 to the power 4.
Yeah, Arpit,
16 pages.
16 pages. So number of bits in VPN, 4. Okay. Good. So let's write 100 in binary. So 100 is 64 plus 32 plus 4, right? So no 16, no 8, 1, 4, 0, 2, 0. Good. So this is the like binary of 100, and last 4 bits are offset. So offset is 4, and this is the VPN. So VPN is 2 plus 4 is equal to 6. Okay, good. So this is how the VPN and offset look. So let's like make a diagram of the memory. So since there are 16 pages, let's assign just one row to each page. So let's say this is the 7th page. So, okay, so this is 0, 1, 2, 3, 4, 5, 6, 14, 15. So these are the 16 pages, and then let's say this side will be the offset. So divide into 4 parts. So let's say this is offset 0, this is 4. I mean the starting address, this is 12. Sorry, this is 8. And this is 12. Okay. So I'm just putting the starting address of the offset. And now this integer 100, which is going to store basically A0, will be at 100. So that is at VPN 6, offset 4. So VPN 6, offset 4, here is A0, then A1, A2, because each of them takes 4 bytes. Okay. So this is how the elements of the array are put in the memory. Okay. So this is VPN 6, 7, and 8. Okay, good. So let's do the. So suppose the program accesses this array in one after the other. First A0 until A9. So what is the first access? Virtual address is 100. And suppose on the first address, okay, so VPN we have calculated 6, offset is 4. Now from the algorithm, it checks whether this VPN is there, check in the TLB. And suppose this is the first time the array is being accessed. So suppose miss, then what it does, insert into TLB translation of VPN 6. Okay, so this is what happens in case of first access. Now suppose second access. So this was for A0, this is for A1. Now virtual address is 104. So if you calculate the VPN, it's going to be 6. Offset is going to be 8 now. And now again, it checks the TLB. And it's going to be a hit. Why? Because for 6, we have already stored the translation. Okay. So similarly for third, for A2, it's going to be a hit. Why? Because the offset is going to be 12 and the VPN is going to be exactly the same. Okay. Now what about the fourth? In fourth is going to be A3. So A3 virtual address is going to be 112. So if you translate 112, it's going to be like 64 plus 32 plus 16, and everything else is 0. So now you get to a new VPN, which is 7, and offset is 0. Okay. So again, it checks the TLB, and this is going to be a miss. Okay. So after the miss, it will insert translation for VPN is equal to 7. And now this has been done for VPN is equal to 7. It has been inserted. So fifth is going to be hit, which is going to be for A4. Sixth for A5 is also going to be a hit, because you see all these are in the same page. Seventh for A6 is going to be a hit. And now the eighth for A7, it's going to be a miss. Why? Because of the same reason. Now A7, you get to a new page. And for A8, you get a hit. And for A9 also, you get a hit. So if you see, it was like how did it look? It was miss, hit, hit, miss, hit, 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 then miss again, and then 2 hits more. Is that correct? Till this time? Yeah. So total, we see that it is 7 hits and 3 misses. Okay. So this is like quantified in something called a TLB hit rate. So here the TLB hit rate is 70%. So basically the number of hits divided by the number of total memory accesses times 100. Okay. So you see that this is of course like non-zero for one thing, right? So it's not that for every memory access now we are doing one more memory lookup. So that is one thing. So that is why this is going to be better. So if it is non-zero, of course, we are getting some speed up. But we would ideally want it to be as close to 0. And this speed up we are getting even though this is the first time we are accessing the array. Okay. So yeah, and we would want this TLB hit rate to be as close to actually 100. So that on every memory access, the like no extra memory lookup is needed, just like everything is found in the TLB. Okay. Good. So now let's see why we were able to achieve this high rate. So any idea that, or I mean, you would have an idea, but can you like pinpoint it that why this was happening? Why the lookups were not like resulting in extra memory references?
Because the memory we accessed was firstly sequential, and there were multiple array elements in one page.
Yes, exactly. So this is also called spatial locality. So there is a name for it. Okay, right? So what does spatial locality mean? That elements accessed are close to each other in the memory. Okay. So, and this happens in case of array. And that's why we were able to make use of it. Okay. So when this happens, then only the first access to a page is a miss. The remaining will be hits. Okay. So this is something, but and from this now, like, can you see something else that okay, what if we increase the page size? Then it will result in like even fewer misses, right? Because now this will be like only the since only the first access is going to result in a miss. Now the array size is more, so there are more hits in that case, right? So page size also becomes a factor. So it plays an important role. So suppose instead of like 16 bytes, if it was like 32 or 64 bytes, then it would be even less. Uh, the miss rate would be even less, and hit rate would be higher. So large page size will be higher TLB hit rate. Okay. Typical page sizes is like 4 KB. Generally, it's not like 16 bytes or something. So these kind of array references are very like efficient. Have very high TLP. Okay. So this results in like good performance. But I mean, of course, not everything is like array access and so on. So there will be some things which are not like sequential access. But if it is going to be sequential access, then it is going to have high. Okay. There's another thing called temporal locality of a program. And so, what do we mean by temporal locality? Any guesses?
Uh, Sir, any memory access that it will be accessed again in near future.
Exactly. Okay. So, if a program accesses memory again in a short duration, then no TLB miss. Okay. So, assuming that the in between translations are can be like kept in the memory in the TLB. Okay. So yeah, so temporal locality is just quick re-referencing you have to define it of memory items in planning. So that was about space, and this is about time, right? So, like any cache, like we'll see like memory caches and so on, and so TLBs also rely on like both these localities to get good performance. So so if a program has these qualities, then it will have high TLB hit rate. Okay. Yeah. So good. So this is what TLBs take advantage of, and I hope the example made it clear that at least the spatial locality. And suppose this array was being accessed again immediately after, like so first you initialize it, then you perform some operation on it, and so on, and then the address is going to be there, so it will not result in any miss. Okay, so now let's see in detail what happens in case of a TLB miss. We have like outlined it, but there are a few more details that we need to take care of. So, so we have seen the hardware based. Okay, so there can be two approaches for it. So first question is who handles it, and as always, there are two answers. Like it can be hardware handled or it can be OS software handled. And the algorithm that I wrote above was a hardware handled TLB. Okay. So because in case of TLB miss, the hardware actually went to the page table, looked at, found the page table entry, and inserted it into the TLB. Okay. So this is the okay. So we are talking about hardware handled for now, and now to take care of a miss in case of hardware handled TLB. So hardware needs to know where exactly the page table is. Okay. And also the format of it, like size of page table entry, etc. To do that. Okay. So on a miss, hardware will find the content of desired page table entry and insert it into TLB. And then retry the instruction. So yeah, so here we in case of TLB misses, after we load the insert the value of the or insert the translation into the TLB, then we retry the instruction, and then it will be a hit, and then the instruction will follow. It will not go into the else part. Okay. Okay, so this hardware thing is or was quite common because, like as the book says, like the hardware people did not trust the like software people too much, so they wanted to perform these things by themselves, and this was there in like its architecture. Okay, but now more common is what is going to be the software managed TLB. So we'll discuss this. So software means, of course, OS, because you don't want to program a user program to manage such a sensitive thing. So now on a TLB miss, the hardware would just raise an exception. And then the OS will take care of it. So basically, in this algorithm, let's go back to the algorithm. So in case of a TLB miss, so the algorithm for this is hardware based. And if we want to write software handled, then all these are going to be the same, the initial instructions. Okay. If hit, then all these parts are same. But in case of a TLB miss, now it will just raise an exception. TLB miss. Right? And then it will just wait for the OS to do the job, and then it will retry the instruction. So nothing. Okay. Yeah. So I hope you understand what I'm trying to say. That instead of doing all this that the hardware was doing there, it will just raise an exception. Okay. So now, but the exception is raised, and now the OS needs to do something, right? And we are learning about OS. So yeah. So now what happens when the exception is raised? Oh, so in case of exception, like always, first pause the correct execution. Okay. Go to kernel mode. Then go to the specific trap handler. So what is this trap handler? This is some code in the OS for the TLB miss. And then look up for the translation in page table, wherever it is, then update TLB, right? And this is, of course, like a privileged instructions, get instruction. And then perform a return from trap to give the control back to the process. And then the process will retry the instruction. So this is what is going to be the control flow in case of a software or OS handled TLB. Okay, but there are 2 points which are to note. First is that this return from trap is slightly different than earlier one. So what is the earlier one? In case of context switch. So can somebody tell how is it different? Like, I mean, any guesses?
The earlier return from trap, it restored the registers, etc. But I don't think this would need to do that.
This would need to, of course, set the registers and so on for the process because it is doing that. And I mean, when the OS is running, it actually goes to some code. So maybe it might have reset the registers and so on. So you might still have to reset the registers. There's one very small but key difference which is there.
Uh, After restoring the register, the hardware will again do the TLB access.
Yeah, so the hardware will do the same thing. Yeah, so it will do the TLB access for the instruction which was being performed. So instead of going to the next instruction, so earlier when the context switch happens, like some instructions are performed and then the program returns, gets control, and the next instruction gets executed. In this case, the last instruction which was tried to be executed, that will get executed again. Okay. So execution starts with the last instruction, not after it. Okay, so for this reason, the PC that gets restored or saved by the hardware. So the program counter saved and restored has to be different from the earlier return from tab. Okay. And also there is another point that okay, now you go to another code and which is the trap handler for this, and suppose that needs like more memory lookups, and then again you come here and you see your TLB miss, and then you need even more lookups and so on, and this might cause an infinite chain of TLB misses and memory lookups. So okay, so any idea how we can solve this problem? Because this is a code, the trap handler. It resides somewhere in the memory. So how do we solve this?
We can keep all of the OS pages in the TLB always.
So the pages are not there in the TLB, but the
Mappings.
translations for OS pages. Yes, right. So one solution, as Arthur suggested, is that keep the or keep some slots in the TLB for the trap handling translations permanently. Okay. So they will never be like, replaced or whatever, and then that can be done. Okay. Another approach is that keep the trap handler in physical memory. That is unmapped. So you directly get like the physical address and you don't need to translate it. It is not paged. It is not like divided into these things. Okay. So unmapped meaning no translation is needed. So these are the two approaches which are there to solve this problem of infinite chain of TLB misses. Good. So there are two advantages of like software managed TLBs. First is flexibility. See that OS can choose any data structure for the page table. And the hardware does not need to know about it. Or like without any specific hardware. Okay. And the second one is simplicity. As you saw that the algorithm for the hardware becomes like quite, the hardware only raises the exception. So the hardware algorithm is simplified. And this is done at the cost of making the OS part more messy. Okay, so now a bit more about what is there inside the TLB. Okay. Just like, so this is not much, but so a typical TLB is like maybe, so book says like 32 bytes or 64 bytes or entries, 32, 64 or 128 entries, and one entry can be like 4 bytes long or something. And a typical TLB is what is called fully associative. So what do we mean by fully associative? That the translation for a particular VPN can be anywhere in the TLB Okay. And the hardware can search for it in parallel. Okay, so you don't need to go one by one looking for the entries. So that is why it is small, so that it can be made fast. Okay, so this is one feature which is like very important for the TLB, that it has to be fully associative, that you can look for the things in parallel, and this allows you to put the VPN anywhere. Otherwise, if it is to be ordered by VPN, you have to do it like sequentially and so on. That will make things slow. So you can search in parallel and just look for the VPN that you're looking for. Okay. So and what is a TLB entry? This is just like a page table entry. So it is VPN, physical frame number, and some other bits. And other bits, just like the last time we discussed about the page table entries, like valid bit, protection bits, dirty bit, etc. Yeah, access bit, and so on. Okay, so this is what is inside a TLB, more or less. So the main point was that the TLB is fully associative. It is very small, and you can search for things in parallel. Okay. Now another question, which is like, so what to do in? I mean, not what to do, what to take care of in case of context switches. So as you see, the TLB has all the entries which are valid translations only for the current process. So during context switch, we need to make sure that the next process does not accidentally use the translations of previous process. Like, so because the TLB can just look like some VPN, some valid bits, let's say, and then let's say protection bits. Let's just write those for now. So suppose it was 10, 100. This is valid, read, write, execute. Second entry was nothing. Let's say third entry was again 100, 170, 1, read, write, execute. Now the hardware gets like, VPN 10. And so this was for process 1 and this was for process 2. But now the hardware has no way to know which one is for process 1 and which one is for process 2. So which address translation? So so this is something we want to avoid, that this should not happen. Okay. So how can this be done? So there are two solutions. At least one of them you can definitely figure out. What can be the solutions for this problem?
We can save this to memory and invalidate all the mappings.
Exactly. So it is called flushing the TLB. On context switch. I mean, we don't need to save it into memory because then, like next time, we have to bring things from memory anyway. So we can just do a like whatever we do in case of normal things. Just look at into the page table and bring back things. Okay. So basically, this just empties it. So set all valid bits to 0. So now nothing is valid, and this can be like done by hardware or software. Okay, but there is one problem with this, which is that every time a process runs, or every time a process runs again, it will result in misses. Okay, so for this, there is another approach called sharing TLBs across. Context switch. So here, TLBs also have a field, have an extra field called address space identifier. Or ASID. Okay, so this is similar to the process identifier. PID, but has less bits. So for all practical purposes, you can think of it as like process identifier. So now it will look like VPN, physical frame number, valid, protection, and then ASID. And now this is going to be fine if this is 10, 100, 1, read, write, execute. Now the SID is going to be different for the two. This is 10, 170, valid is 1, read, write, execute, and this is process ID is 2, so there is no confusion. But now the so this will cause no confusion now. But now the OS's job is increased and it will need some hardware support also. So OS needs support in terms of another register for the ASID and should restore it while doing context switch. And now, like after this happens, now this also allows like two different processes to map to same physical frame number. Okay, so okay. Come on. All right. Okay, so yeah, so what I was saying that now this can happen that suppose VPN 10 of process 1 goes to frame number 101, it is valid. So suppose it is read and execute, and process 50 again the VPN of 50 from process 2 goes to the same page, is valid, read execute. So this is possible, and this will allow us to do what? What does this mean?
Code sharing between
Yeah.
processes.
So sharing of physical memory between processes. So both processes are sharing this physical frame 101. So this allows for that. Okay. And this will reduce the number of physical pages in use. There is one more small topic which is called, which is the replacement policy for TLB. And like since TLBs are very small as we saw, so after when we want to insert something, after being full, insert needs to remove something. So what can be a very understandable policy to remove? Which pages to remove? Okay, we don't have much time. I need an answer. Which translations to remove?
The oldest ones, the
Yes,
first ones which are initially inserted.
exactly. So that's like whatever is not used, the the oldest one. The technical name for it is least recently used, or LRU. Okay. So uses time locality, temporal locality as a thumb rule. So something is not recently used, then less likely to be used again. So can be evicted. Okay. And another approach is just random. So evict a translation randomly. The advantage of this is simple. and avoids some corner cases of least recent use. And what are those corner cases? Let's just have 1 minute. Let's just go through that. So what is the corner cases? Let's see that. So suppose you have n slots in the TLB and the program accesses n plus 1 pages in loop. Okay. So what will happen? So for the first one, it will be a mess but after n are there, then it accesses the n plus 1th one. Okay. So it will remove the first one and put it there because that was the least recently used. After that, it will put the 1 and now it will remove the 2 and will put it there. Then it will do 2. It will remove the 3 and put it there. 2 it has just removed, so it does not know what to do. So then it will like result in all misses. Okay. So this is like one corner case of least recently used, and this can be avoided by doing a random mode. Okay, is this case clear? I hope it should be. It's not that hard to understand. Okay, so any questions about today's lecture? We are done. So this is what we like. This is what I wanted to do today. And in the next lecture, we'll be talking about another problem of page tables that size is large. So there were two problems, if you remember from the last lecture. One was the size of the page tables, and the two was that they slow things down. So in this lecture, we looked at the slowing down part, and we saw how to speed things up using TLB. Next time, we'll look at what to do with the size of the page tables, which are very large. Okay. Any questions about today's lecture? Or anything? Okay. If not, then thank you, everyone. See you on Thursday.